Hello, young physicists. Ever wondered why a balloon expands when heated or why your pressure cooker hisses more as it gets hotter? Well, the secret lies in something called the kinetic theory of gases. Let's rewind to the 1600s, no pressure cookers yet, but a brilliant scientist named Robert Boyle was busy playing with air and tubes. In 1661, Boyle discovered that when you squeeze a gas, its pressure increases, giving birth to Boyle's law. Pretty neat, right? Later, Isaac Newton and a few other curious minds started thinking, what if gases are made of tiny bouncing particles, like invisible ping-pong balls in a jar? That idea became the seed for the kinetic theory. But the full atomic theory? Oh, that took more than 150 years to prove. These early thinkers basically said, let's explain air, pressure, and heat not as magic, but as motion. That's how mechanics and thermodynamics got married, and their baby was kinetic theory. So yes, Boyle and Newton might not have known it, but they were actually the first DJ mixing physics and atoms long before quantum beats came along. Now that we know the story, let's peek inside the gas itself. Imagine zooming into a tiny box of air. What do you see? Millions and millions of molecules zipping around randomly, colliding, bouncing, and doing a never-ending dance party. The kinetic theory says gases are made of these fast-moving particles that almost never stick together. The forces between them? Practically zero, except when they bump into each other like bumper cars at a fair. Between these collisions, each molecule moves freely, minding its own business. But here's the beauty, the average kinetic energy of these wild little dancers depends only on temperature. The hotter the gas, the faster they move. In fact, the average kinetic energy per molecule equals 3 by 2 kT. That's 3 divided by 2 times the Boltzmann constant K times the temperature T. So, next time you feel the warm air from your hair dryer, remember, those gas molecules are just hyperactive dancers fueled by heat energy. Fast forward to the 1800s, meet our two physics rock stars, James Clerk Maxwell and Ludwig Boltzmann. These legends took the random dance of molecules and turned it into mathematics. They showed that pressure, temperature, and all gas laws could be explained by the motion of molecules. Pressure? It's just those tiny collisions hitting the container walls. Imagine a million microscopic basketballs bouncing inside a box. That's your gas pressure. Maxwell and Boltzmann also gave us the idea of statistical mechanics, the art of handling huge crowds of molecules. And from that came one of the coolest results, the Maxwell-Boltzmann distribution. Their famous equation says P equals 1/3 nmv squared bar. That means pressure depends on how many molecules there are, n, how heavy each one is, m, and how fast they move, v squared bar. So, the next time you open a soda can, just know that hiss of air is Boltzmann and Maxwell's masterpiece in action. The kinetic theory didn't just stop at explaining pressure and temperature, it went further. It gave us a molecular interpretation of every measurable gas property. It confirmed all the gas laws we knew, like Boyle's, Charles', and Avogadro's, and explained why equal volumes of gases have equal numbers of molecules. Even better, it told us why some gases have higher specific heat capacities than others, because energy gets shared among different modes of molecular motion. And here's the cherry on top, kinetic theory relates viscosity, conduction, and diffusion to how big the molecules are and how often they collide. There's a neat formula, viscosity eta equals 1/3 times density ρ times mean molecular speed V bar times mean free path L. So, when you smell your mom's cooking from another room, that's diffusion in action, a direct gift from kinetic theory. Now, every great theory has its boundaries. Kinetic theory assumes all collisions are perfectly elastic, like super bouncy balls, and that molecules don't pull or push each other unless they collide. This works beautifully for ideal gases, but not so well for real ones. When gases are squished under high pressure or chilled to low temperatures, molecules start to feel each other's presence and things get messy. Also, kinetic theory doesn't account for quantum effects. Those become important only at extremely low temperatures. Still, for most situations, from your classroom air to jet engines, the kinetic theory is spot on. As shown in the diagram, the molecules move randomly, bouncing off each other and the container walls. So yes, it's idealized, but it's one of those good enough to explain almost everything models in physics. Alright, time to flex our physics muscles and derive the famous formula for pressure. Imagine a cube-shaped box of gas with side length L. Inside it, N molecules, each of mass m, are zipping in all directions. Let's focus on one molecule moving along the x-axis with speed vx. When it hits the wall, it bounces back, changing its momentum by 2 meters vx. How often does it hit the same wall? Well, it travels a distance to L to come back, so the number of hits per second is vx divided by 2L. Hence, the force on the wall from one molecule equals mvx squared divided by L, add up all molecules and average over all directions, and we get, drum roll, P equals 1/3 nmv squared bar. Where n is the number of molecules per unit volume, m is molecular mass, and v squared bar is mean square speed. This beautiful relation tells us that pressure depends directly on molecular motion, faster molecules, higher pressure. Simple, elegant, and completely mind-blowing. So, what did we uncover today? That gases aren't empty space, they're bustling cities of moving particles, bouncing, colliding, and obeying Newton's laws. Temperature? That's just a measure of how energetic these molecules are. Pressure? The push from their collisions with the container walls. Thanks to Maxwell and Boltzmann, we now have the perfect bridge between the unseen molecular world and the gas laws we measure in the lab. The key equations, P average equals 3/2 kT and P equals 1/3 nmb squared bar, connect energy, motion, and matter in one elegant sweep. So next time you open a soda can or watch steam rise from your tea, remember, it's not magic, it's kinetic theory in motion. And that's a wrap for today's concept. I hope you had fun exploring the microscopic mayhem of gases. See you in the next session, where we dive deeper into the molecular nature of matter. Until then, keep questioning, keep observing, and keep thinking like a physicist.